So I'm going to be working problem number 20 from your book. Question is talking about a car that's traveling at a certain speed and hits a bridge abutment. The passenger kind of slams into an airbag and comes to rest. And it wants to know what the magnitude of the force is if we assume it's a constant force that acts on the passenger's upper torso. So this is just a pretty... It seems fairly straightforward, but the first thing I'm going to do, though, to make sure I don't start just trying to grab equations and plugging in numbers, is I'm going to draw a little bit of a sketch. So here I have my guy, and here's his upper torso, and he's traveling in his car, it turns out, but so I could kind of roughly sketch the car here about him. But we don't really care too much about the car itself. We want to know about the force acting on the driver. Oh, sorry, a passenger, actually. Sorry, not the driver. It doesn't say the driver, it says the passenger. He's traveling with an initial speed of 57 kilometers per hour. And note that not only am I sketching down the value of the velocity, and I might label that as an initial velocity because I know that's the velocity when it's first moving, but I'm also drawing an arrow which is going to show which way he's initially traveling, and kind of gives me a sense of just some type of vector length that might be helpful in looking at the rest of the problem. It may be not. He's going to hit an abutment, and the car moves 67 centimeters. Okay, so once this is right when it hits. So some initial picture is it hits the bridge abutment, and then at some time later, this is the initial time equals 0, and then at some other later time, the car is maybe all crumpled up on the bridge abutment. It bent a little bit now. It bent over, and it bent over some distance of, it traveled a distance of 67 centimeters. I'm not sure exactly how this sketch is going to look, but it's kind of... Here's our guy. Now he's not moving anymore. He stopped because there was an airbag that came out that helped him slow down. And he traveled 67 centimeters during the course of that in order to slow down. So while he was slowing down, the distance that he kind of traveled was 67 centimeters. So actually I'm going to sketch that back over here just so I see it. I mean, he's traveling 67 centimeters in order to come to this stopping position that he's going to end up at, that we kind of pictured over here in our second frame. We know that his mass, it tells us his mass is 43 kilograms, and that's the only information it tells us, and it wants to know what is the force. And although it doesn't ask for the net force, what it really is, we're really looking for is the net force acting on the passenger. Because that's going to tell us something about the acceleration, right? When it's asking us about force, it's giving us information about his mass. We know how these two are related. We know that the net force is going to be equal to the mass times the acceleration. And specifically, we know that there's even a vector relationship, that the net force and the acceleration act in the same direction. So since we don't know what the net force is, we do know what the mass is. Many of you, what I've seen on a lot of the homeworks, is that you start plugging in numbers right away before we solve anything. And something I'm going to encourage you to do, and something that I'm going to try to model, is not putting numbers into our equation until the very last moment. So even though I know what 43 kilograms is his mass, I'm not going to go plugging that in, right? I'm going to leave it as an M, so that I don't lose track of what that number means. So if I wanted to determine what the net force is, I know what the mass is already, but I don't know what the acceleration is yet. It wasn't given in the problem. Hopefully what you can kind of see is that there is some information given in the problem. At this point, his final velocity is equal to 0 kilometers per hour. Right? Initially, it was 57 kilometers per hour. So now we have an initial velocity and a final velocity, and we know the displacement that it took for that acceleration to occur, the acceleration in the negative direction. And we can relate these things. We can go find our kinematic equation. This is all in one dimension. So final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the displacement. This is just simply motion in one dimension, so I'm going to put a delta x here, but more broadly this should be delta r, right? But I'm just going to leave it as delta x since it's in one direction. Our final velocity is going to be equal to 0 kilometers per hour. Our initial velocity is 57 kilometers per hour. The acceleration is the information that we're looking for, and we know that the displacement is in 67 centimeters. So I'm going to start plugging in my information. So we have 0 kilometers per hour. Notice I'm using units throughout my relationship as I plug it in. The initial velocity is 57 kilometers per hour, and that quantity is squared, plus 2 times the acceleration. And I should be a little more careful with this, that this is technically still, even though it's in one dimension, this is still a vector quantity. It can still have a positive or minus, a positive or negative value. And the displacement is 67 centimeters. Okay. So when I start to calculate this, I'm going to square this value and then subtract it. So it's going to be minus 57 squared kilometers squared per hour squared. And that's going to equal 2 times this value of 67 centimeters times the acceleration. And then when I divide through both sides, I'm going to have 57 squared kilometers squared per hour squared divided by 2 times 67 centimeters. Now, one of the reasons it's so key that we keep the units in, one of the things that can be extraordinarily helpful, is that we should be able to see right here from this expression that if we tried to just calculate these numbers, take 57 squared, that we not worry about what they actually mean, but simply do the mathematical operation of take 57 squared and divide by 2 and then divide by 67, we would get a numerical answer. But we can tell, because we left the units in, that that answer would be pretty nonsensical, because here we have kilometers squared and we have hours over hours squared, and then we're dividing by centimeters. And so our acceleration would be in units of kilometers squared per centimeter per hour, right? That's not a unit that we're familiar with. There are no units that we deal with that look exactly that way. We need to have them in SI units. So what we need to do is we need to either convert this value into centimeters or this value into kilometers, or we can convert both of them into meters or something like that, right? So we could do one of those things. This is actually 67 centimeters is 0.67 centimeters, which would be 0.67 times 10 to the negative third kilometers. Oh, there's also a minus sign here I forgot to add in. So, ignoring that for a moment, right, we'd have negative 57 squared kilometers squared per hour squared divided by 2 times 0.67 times 10 to the negative third kilometers. And you can do that as a conversion. I kind of did it in my head a bit, but you can double check that with your calculator. And now when we divide through, our kilometers squared are going to cancel, and we'll get kilometers per hour squared, which if we wanted that in SI units, we would want meters per second squared. But it's possible that we could, since the problem gave all this information in kilometers per hour, that we could just use that information. So without actually plugging all these numbers in and solving it, you can do that with the calculator yourself. That does tell us a value of the acceleration. It also tells us it's a negative value, which means that what happens when it's a negative acceleration, it means that the change in the velocity is going to be negative. So here we have an initial velocity, which is to the right, in this direction, and then we have a final velocity, which is 0. So that would correspond to a decrease in the velocity, right? A negative change means a decrease in the value, which is what we'd expect to see based on our context of our problem. Now that we have this value calculated for acceleration, down here, we can simply take that value for acceleration and plug it into our relationship here for our Newton's second law equation. So the net force is going to be equal to 43 kilograms times a negative 57 kilometers squared per hour squared divided by 2, oops, bumped the camera, 2 times 0.67 times 10 to the negative third kilometers, and that's 10 minutes.